Okay, so since this didn't align properly, I'm going to actually erase this, and I'm going to show you how this equation gets figured out. So if density is, what do we say? Pressure times the molar mass divided by RT. If I wanted to get molar mass by itself, the first thing I'm going to do is get rid of the stuff in the denominator. So since that's being divided, I'm going to multiply. And I do it on both sides. So we end up with density times RT equals the pressure times the molar mass. Now, we want to get the pressure out of the way, so I'm going to divide. So we end up with the density times RT divided by P, and over here, the P goes away. So we just have molar mass. Now, sometimes density isn't directly given, but I know that density is the mass divided by the volume. So I can also write this equation to be the mass times RT over volume times pressure. And that'll equal the molar mass. Okay, so this form and this form are both useful. If I have a mass of 5, wait, that's not a mass, what? That is supposed to say volume, I think. Yes, that's the mass. Okay, so the mass is, oops, there we go, 8.491 grams, and the volume is 5.200. So since they're giving me a volume and a mass, I'm probably going to use the second version of this because it has volume already and it has mass in it already. So I'm going to say my molar mass equals the mass times RT divided by VP. So MRT divided by VP. Okay, so I have volume, I have mass. It doesn't tell us the pressure and temperature directly, so we're going to assume that it's standard temperature and pressure. That's what it means, standard. So if the problem doesn't directly give us the info, we're going to presume STP. So the temperature then would be 273 Kelvin, and the pressure is 1 atmosphere. And of course, we still know that R is just that constant. Okay, so let's plug it in. So molar mass equals, the mass is 8.491 grams times R times T. T we said is 273. All of that divided by the volume of 5.200 liters, and also divided by pressure, which is 1 atmosphere. So let's cancel whatever cancels. Let's see, so liters, atmospheres, and Kelvin. So that leaves us with grams on the top of this fraction and moles on the bottom, so grams per mole, which is a molar mass. So we set up the problem right. I'm going to put 8.491 in the calculator times 0.0821 times 273. Divide all of that by 5.2. And so we have a lot of significant figures in our data. We have like 4 here and 4 here. So we're going to put 4 in our answer. So the molar mass is 36.598 on my calculator. That would be 5 figures. So I'm going to say 36.60. And the unit is grams per mole, which is molar mass. So that works out. So the next thing is to remember what the word stoichiometry means, and that's what we did as a review for the physics lab. We knew how much baking soda there was, and we found a chemical reaction, and we can use that to convert to how much citric acid you needed. So in the same way, you can do stoichiometry with gas problems. It turns out you could do it the same way we did before. So if you have a problem, say where, maybe you make some CO2 like we did in lab, right? It made CO2 and citrate. I'm not going to write the whole formula for citrate. Sodium citrate, actually. But this is the only gas in the entire process. But if I know how much baking soda there is, I can calculate the moles of that. And from there, use a balanced chemical reaction to go to moles of CO2. And from there to grams. But when we're talking about gases, sometimes it's interesting to know how many liters that gas occupies, because we generally have a hard time weighing gases. They have a tendency of escaping and being difficult to control. So knowing the volume is a much easier way of thinking about it. So once you get to moles of CO2, you could then use the relationship that you already know between moles of gas and the volume. Okay, so let's say, for example, we had 10 moles of CO2. If I want to know how much material that actually is in a useful number, I'm going to use this conversion factor, 22.4 liters for 1 mole. So that means there would be 224 liters of CO2. That's a lot. That's enough to make enough fizzy Kool-Aid for like the whole school. Okay. So this figure comes from your book, and it summarizes all of the stoichiometry that you know. And I think this is a really, really handy way of studying. If you can identify where you're starting on this graph, it's usually one of the yellow boxes. Then you can sort of use this like a map to help you figure out how to get where you want to go. So for example, if I started with grams of citric acid, I can get to moles of citric, and from there, I can figure out the volume of the gas. That's kind of what we just did. Or, that was moles of citric I said, but if it was starting with grams of CO2, you could go to moles of CO2 and then to the volume of CO2. On the other hand, if it was citric, I could go grams of citric to moles of citric and then use the balanced reaction to get to moles of CO2. And I could either go to grams or I could go to the volume of the gas. Okay. In general, we're given things that are on the macroscopic scale, things like grams or volume, and we have to use our knowledge of chemistry on the particle level to convert from, say, reactants to products. And then from there, we want to go back to a macroscopic quantity, something we can actually see and measure. So this kind of graphic is really helpful in doing your homework. So keep it handy. Okay, so our last problem today is a gas stoichiometry problem. So they give us a balanced reaction, so we don't have to balance it, it's already there. And they want us to calculate how many liters of N2 need to be put in to react with 12 liters of hydrogen gas. So we're starting with 12 liters of hydrogen. And you could figure out how many moles this is. Let's work that problem that way. So we're going to go, let's see, 1 mole for every 2.02 grams. Well, okay, wait, grams doesn't cancel. So then I need that relationship between the liters. Go back here. The liters need to cancel before I can even get close to grams. So there. Now we have moles, and then I know that, say, let's back up. So the answer there is 0.5357 moles of H2. So if I wanted to figure out how many moles of N2 to add, then I take that number. Right? oh, whoops, sorry, moles of H2 there. I want to convert it from H2 to N2, so I'm going to use the balanced reaction. Right, so I got to get rid of H2, so I'm putting that on the bottom. We've got 3 moles of H2 there, and 1 mole of N2. My H2 goes away, and so I'm going to go 0.5357 divided by 3, and we get 0.1785, which I'm going to write as 8. It says 857, so I'll go 8 to 6. So now I know how many moles of N2 need to be added, but it tells me to find liters. So I guess I'll use my same relationship between the moles of a gas and the volume to figure out how much in liters. This turns out to be 4 liters. So C is the correct answer. So you can do it this way. This is the same stoichiometric process that we used in 111 and we'll continue to use. And it works very well. The only thing new is this idea that there's 22.4 liters in 1 mole. Now, there's just a little problem with that. We assumed when you say 22.4 liters, that automatically means at STP, but this is not STP. So maybe that's not the best choice. So if I have volume, temperature, pressure, then I could calculate moles using PV equals nRT. Okay, so divide by RT to get N on its own. And so we get here N equals the P, which is, let's see, 8 atmospheres. And we said the V, which is 12 liters, divided by R times temperature, which is conveniently already in Kelvin. So after I punch that all into my calculator, I find out there's 3.29 moles of H2. And I can convert that to N2 using the balanced reaction again. So that means that I would have 1.0979 moles of N2. And then I got to plug that back into PV equals nRT and find the volume. So this time, instead of dividing by RT, I think what we want to do is divide by P. Okay, so I'm going to clear the bottom out. All right, so we get the volume equals 1.098 moles times R times T, which is still 355. All of that divided by 8 atmospheres. And so if we put all this in the calculator, we find that the volume is 4 liters again. Okay, so apparently there's 2 ways to solve that problem. Okay, so apparently when you punch that into your calculator, what you find is the answer is 4 liters again. So apparently there's 2 ways to solve that problem. You can solve it using the ideal gas law like this, or you can solve it using stoichiometry like we just did. Both of those are pretty time intensive though, so let's see if there's even one more way to do this. I'll give you a hint, there is. So if I know there's 12 liters of H2, it turns out that these stoichiometric ratios from the balanced reaction can be applied directly to the volume of a gas because our conditions are not changing. It's always the same temperature and pressure in this problem. So I can just take the ratio from the balanced reaction and get the answer really quickly. This only works if temperature and pressure are constant.